to Group 8's electric motor lab report. The main question that Group 8 had while doing this is that how does increasing the strength of the magnetic field affect the magnetic force? And so some things we knew before coming into this is that the equation for the magnetic force, which equals the charge times the velocity crossed with the strength of the B field. And then one thing that's also known as the right-hand rule, where each finger is a different component of that above equation, and that we can figure out the direction of a third component once we know the direction of the other two.
I'm going to talk about the models that we've created based on our experiment. In the first picture in the upper right-hand corner is our system schema, and there's an electric force, as you can see, between the battery and the wire, a magnetic force between the wire and the magnets, and then a contact force, a magnetic force, and an electric force between the battery and the magnets. In the lower right-hand corner, you can see that there is our free body diagram picture. So our velocity and current, which is based on point A in figure 1, in the next slide, is going to the left. And this current is created by the battery. And then the magnetic field is pointing down, and this is created from the magnets that are connected to the battery. And since there's a magnetic field, there has to be a magnetic force, which we find based on the right-hand rule. And this magnetic force is coming out of the page at you. Before I continue with this slide, I'd like to say that in our free body diagram, in our last slide, that is referencing point A in figure 1. So continuing on explaining the figure, so in figure 1, at point A, the magnetic field is going down in the blue, the current is going to the left, and therefore the force is going out of the page using the right-hand rule. At point E, the magnetic field is going down in the blue, the current is going to the right, so the force is going into the page. If it's going into the page here, it's going to push the wire back, and at point A, if the force is coming out of the page, it's going to push the wire towards you, creating that spinning motion. In figure 2, the wire has moved a quarter way around the battery, so at point A, the current is going into the page, the magnetic field is going down, so the force is going to the left. And at point B, we cannot see it, it's behind the battery, directly behind A, point A, so the current is going out of the page at you, the magnetic field is going down, and so the force is going to the right. And then in figure 3, it's the same as figure 1, but point A and point B switch because the wire has already moved all the way around the battery.
In our experimental design, we used 1D battery, 2 copper wires, and several small magnets. The magnets were attached to the bottom of the battery, which we will call the negative end. In this trial, we are assuming that the battery has the exact same voltage, the magnets are of all the exact same strength, and friction is the same across every run. Now, we can observe the number of times a wire goes around the magnet, and we can use that to determine the velocity. And since we know that the velocity is directly proportional to the force, when the velocity increases, so does the force. We conducted 4 runs of our experiment. In each run, we increased the number of magnets by 2. Each run also had 2 trials in order to improve data quality. For each trial, we counted the number of spins in a 5-second time interval. From this data, we can observe that there is a large magnetic force pushing on the wire when more spins are recorded.
So I'm going to talk about some of the conclusions we had from this lab report. And the main conclusion we had was that as the magnetic field increased in strength, the magnetic force also increased in strength. So that the magnetic field and the magnetic force are directly proportional. And we figured this out by the more magnets we had, that meant that we had a stronger magnetic field. And so when we had a stronger magnetic field, the velocity of the wire was greater. And so some errors that we might have encountered was that the battery started to die over time, and that changing the wire each time could affect how much friction there was, and then we could have miscounted the number of spins. However, we did multiple trials in order to try to account for those errors.